So I'm reading the
Yes, sir.
question.
Yes.
Question says that. Okay, a charged sphere has an electric field just like that of a point charge of the same total charge located at its center. What is the electric field of a long conducting cylinder like? Hello? So go through, I think let us give ourselves 1 minute. Yes, Mr. Katito.
So I think it's cannot tell the information given.
We cannot tell from the information that has been given. Okay, what do others say? What do others think? What do others think? Okay, so if others don't think anything, I'll skip this slide, and then when you think something, then you let me know. Okay? Agreed? So no one, anyone?
I think the answer is B.
The answer is
D.
the answer is D. Why do you say so?
My answer is C.
The answer is C. Okay, so let us just try our answers. Those who are saying D, why are you saying D? Huh? Those saying D, can we just try our answers? And maybe if the ones saying C are ready, they can tell us why the answer is C. Huh?
So the reason why I'm saying that the answer is B is because the cylinder can be treated as a continuous of charge, being of charge.
Okay. So just give me 1 minute.
Hello, sir.
Hello? Okay, so here the thing is that, look, do you remember the first point? We say that when you have a charged sphere that has got an electric field, then you can treat that charged sphere like a point charge. Do you remember that? Do you remember that point? Do you remember that what we had learned in one of the earlier lectures? That if you have a sphere that has got charge, it is as good as treating that all of that charge as being concentrated at the center of that sphere as a point charge. You remember that? So if we why are we considering it to be a point charge? Because of the symmetry consideration. You see that a cylinder is a sphere will be round, and the point is also round. Now, if you have a cylinder, can you think of a one-dimensional configuration that, you think of a cylinder that is charged here. Can you think of a one-dimensional configuration that will have the same symmetry as a cylinder? That will be a line. That will be a line of charge, and that's why our class said that the answer is C. So it means that we can treat a cylindrical distribution of charge as if all the charge were concentrated in a line that is along the axis of the cylinder. Okay, so I think we are running out of time in this session. We are running out of time in this session. I'm going to close it, and then we meet on the other side where we now start discussing something else. Okay, so now let us try to apply Gaussian
Yes.
Gauss theorem now to a uniform sphere of charge. A uniform sphere of charge. So the procedure again is the same. We want to find, if you have a uniform sphere of charge, imagine that you have this. This is a uniform sphere that has got charge that is uniformly distributed. Then we say, what is the electric field inside the sphere? And what is the electric field outside the sphere? I think I'll repeat what I've just said. You've seen that there is a sphere. There is this sphere. It just ends here. These dots that you can see are the charges. Okay? So if you have that charge distribution, then we ask ourselves, what is the electric field inside that sphere and outside the sphere due to that charge distribution? Okay, so we start with, let us start with inside the sphere. It means that, remember the volume charge density? The volume charge density is given by what? The total charge over the volume. Remember that equation, eh? So if you have a sphere like this one, then what is the volume of a sphere? Then it is 4 over 3 pi r cubed. Yeah, you remember this? So it means that the volume charge distribution, it will just be given by Q over 4 over 3 pi r cubed. You see that the radius of this sphere is from here up to here, which here is capital letter R. Okay, so now what is the electric field pattern? What is the electric field pattern due to this configuration? Remember what we had said, that the electric field is always perpendicular to the surface at any given point. The electric field, so if I have to draw the electric field lines, then it will have to be perpendicular, so it will be radial. It will be going outwards from here to here, from here to here, it will be radial. So now, can someone tell me, in that particular case, what will be the angle between the electric field lines and the area vector? What will be the angle between the electric field lines and the area vector? Look at the diagram carefully. It will be what?
90.
I think I'll not accept the only one person. Okay, thank you very much, madam. The angle will be 90. Okay, is that so? Why are you saying 90? Why did you say 90? No? Okay, now let us give it to Mr. Kakito again.
Because the area vector, it's normal to the surface, and the electric field are perpendicular to the surface of the enclosed charges.
Okay, so that's exactly the way it is. So what we are the area vector will be perpendicular to this surface like this. That is the area vector. Now what is the electric field? Will also, because the electric field is also perpendicular, then the electric field at this particular point will also be perpendicular. So now what can you say about the angle between them? Angle between them is 0. I hope we are all seeing that. So the angle between them is 0. That's the important thing. Why do you want to find the angle between them? Because you want to find the flux. Remember, flux is electric field times the air times cos theta. So since the cos theta, you have identified that it is 0, and you know cos 0 is just equal to 1, it means that this dot product, it will just become a normal product between the electric field and the dA. And since the electric field is a constant, you are going to pull it out of the integral so that you just remain with the dA. And the dA, when you integrate it, what you come up with is just the area, which is A. So you have this formula. So you have epsilon naught, which was here before, the electric field, which I had pulled out of the integral. And now this area, if I integrate this area, I come up with a total area of the sphere. In this case, remember the total area of the Gaussian surface. I've taken the Gaussian surface. I've taken the Gaussian surface to be inside. Here it has got a radius. If the Gaussian surface is inside, it has got a radius of r. Then you remember the surface area of the sphere is 4 pi r squared. This is the surface where the electric field is passing. So this is the left-hand side. This represents the flux. Now, what is the charge enclosed? What is the charge enclosed? The charge enclosed is this, the charge that is within this. Charge enclosed is the charge that is here. So that can be written from this formula. If I make charge subject of the formula, then I can just have rho times 4 over 3 pi r cubed. So this is what is here. So the Gaussian law, I'm evaluating the left-hand side. That involves the flux. In the right-hand side, that involves the charge that is enclosed by the Gaussian surface. So from here, a number of things are going to cancel. You see that the pi r squared is going to cancel in such a way that what we just remain with is 1 r there. And when you make electric field subject to the formula, then you just see that the electric field is just given by it. So it shows that at all points that are inside, at all points that are inside the sphere, at all points that are inside the sphere, then the electric field can be given by this formula that is here, where rho is the volume charge density. Any questions? Any questions? Okay, so now this formula that we have found is for electric field that is inside. We had taken the Gaussian surface to be inside the sphere that has got a charge. So by the way, maybe before we go, I would want to just point out that what do you think is going to happen as you are increasing the radius? What do you think is happening to the electric field? Remember, this thing is just a constant because the rho, which is the charge density, is a constant. The 3 epsilon naught is also a constant. So my question is that as you increase the radius, what happens to the electric field?
Electric field also increases.
It also increases. So it means that inside.
It also increases.
Exactly. So it means that inside this sphere, as you move away from the center, it means that the electric field line will be directly proportional to the radius of the sphere. So if you have a sphere which has got charge that is uniformly distributed, then as you go outside, then the electric field will increase. It will be directly proportional to the radius. Now, what of outside? What is the electric field outside this sphere here? What is the electric field outside? So you construct a Gaussian surface that is outside like this. Construct a Gaussian surface that is outside the sphere. You see the sphere just ends here, ends up to here. But then the Gaussian surface, we have constructed it outside. It has got a radius of r. So again, in this case, the r is actually greater than the r. You see, this capital letter R is the radius of the sphere. This small letter r is the radius of the Gaussian surface. So the small letter r in this case is greater than capital letter R. So we apply Gauss' law again. What is the flux? The flux, as usual, we are going to follow the same steps. It's going to be here. But on the right-hand side, we are saying that what is the charge enclosed? You see, have you noticed that this Gaussian surface, since it is outside, it has now enclosed all the charge. It has enclosed the total charge. that is on this sphere. So it means that the enclosed charge is just equal to the capital letter Q. And if you make E the subject of the formula now, you make E the subject of the formula, then the electric field will just be given by Q over 4 pi epsilon naught R squared. Okay? So now if you look at this equation very carefully, then you realize that this electric field is basically the electric field due to a point charge. Just remember, this 1 over 4 pi epsilon naught is just basically K. So the electric field is just K times Q over R squared. So in this case, the electric field is the same as the electric field due to a point charge, which is at the center of the sphere. Okay, so we can, this result that we had obtained, I think, from Coulomb's law, we have come across it again from Gauss's law. So if you have a cylinder, if you have a spherical distribution of charge, it means that outside that distribution, the electric field will be the same as the electric field line, the electric field that would be if that entire charge distribution was to be concentrated at the center of the sphere. Any questions? Any questions? Okay, so no questions here. So
You can proceed, sir.
Pardon? Is that a question? No questions, right? Okay, so since there's no question, let us try out this question together. The question says that the drawing shows 3 cylinders in cross section. So these 3 drawings that you can see here, it shows the cross sections of 3 different cylinders, each with the same total charge. So each has the same size, each has the same size cylindrical Gaussian surface. So you can see that the Gaussian surfaces are shown in dotted lines here. So each of these cylinders have got the same size of the Gaussian surface. So the question is, rank the 3 according to the electric field at the Gaussian surface, starting with the greatest. So the question requires us to rank the electric field of these 3 at the point of the Gaussian surface. Anyone?
The answer is B, sir.
The answer is B. So it means that the electric field is greatest here, and then followed by here.
No, sir.
Pardon? So you're saying that the electric field here will be greatest here on this surface, and then followed by this surface, then followed by this surface. Why have you said so?
The answer is A, sir.
The answer is A. So it means that the electric field line is, the electric field is greatest here, and then followed by here, and then it is there, the least here. Is that what you're saying?
Yes, sir.
So why are we saying that? So I think there's another school of thought that the answer is C. Okay, now I'm not getting the explanations to this.
I say the answer is C because we say the electric field depends on the radius, and all the 3 circles have got the same radius.
Come again. You said that the what?
We say the electric field increases as the radius increases, and looking at all the Gaussian surfaces, they've got the same radius. So I think the answer is C.
So we said that the electric field line, the electric field is proportional to the radius. Okay, so what do others think? Let me get
It's
the
A,
people who
because
said A and B. Let us support the answers.
it's A because the area in which the electric field is passing there It has a small radius, hence the greatest in the electric field. So that's one who have the
tell
greatest
me, have you
electric.
pictured what is happening? No, this one here is just a cross-sectional area. It's like, this is a cylinder. Have you noticed that this is a cylinder? So it's like they have just cut. No, the three cylinders have been cut. So what they are just showing us are the cross-sectional areas. Have you noticed that?
Yes.
So this is a cylinder, a small cylinder. It has got a smaller radius, but it goes right inside the screen and it comes out. So what we have just been shown is the cross-section area. When that cylinder has been cut, what is the cross-section? And what is the cross-section here? What is the cross-section here? So now the question is that what is the electric field at the point of the Gaussian surface? So it means that what is the electric field here, for instance, compared to here, compared to here. So now if someone says that what is the direction of the electric field lines in this case? If you have to sketch the electric field lines, they'll be like how? Huh?
They'll be pointing outwards.
They'll be pointing outwards. I think that is very good. The electric field lines will be pointing outwards. So now let us compare the electric field lines that will be passing, the flux that will be passing here, the flux that will be passing here. Now, have you noticed that this Gaussian surface has enclosed everything? It means that the entire charge is enclosed by the Gaussian surface. Have you noticed that? The entire charge has been enclosed by the Gaussian surface. Have you noticed that?
Yes.
Yes. So if you apply Gauss flux theorem, on the left-hand side of Gauss flux theorem, remember you have this. On the left-hand side, you have the electric field and the area. Remember, this area here is the area of the Gaussian surface. Now, the Gaussian surfaces are the same. So the electric field and the area where the electric field is passing, which is the area of the Gaussian surface. And on the left-hand side, you have the charge that is enclosed. Now, all those, you see that all the charge is enclosed, whether the Gaussian surface whether the cylinder itself is small or big, but everything has been covered by the Gaussian surface. So what can you say about the electric field? The electric field will be the same. The electric field will be the same, and that's why the answer came out to say that it will be a tie. The electric field will be the same. Now, if we talk about this is different. This is different. You see, here we had the charge distribution was a sphere and not a cylinder. And you see, the Gaussian surface was inside here. So the Gaussian surface is not covering anything. So we came up with this expression. So where we were trying to explain that the electric field is proportional to the radius is where the Gaussian surface has not covered all the charge. So it means that when you take a smaller Gaussian, when the R is smaller, it means that the Gaussian surface is smaller. So when the Gaussian surface is smaller, it means that it hasn't covered, it means that the charge that has been enclosed is smaller, and hence this R is also smaller. I hope we are making sense. Any questions regarding this before we proceed? So no questions. Now, when we go to a non-conducting sheet, we are going to repeat the same thing that we had done, but assuming that we have a non-conducting sheet. This sheet is non-conducting. What does it mean? What do we know about a non-conducting sheet? So a non-conducting sheet with a uniform surface charge density has the same geometry as that for a non-conducting plate. So we use the same Gaussian surface. So we use the same Gaussian surface that we had used. But look at this point. The only difference is now that one end cannot close in a conductor. So the flux is at both ends. Now, you see, what did we say about a conductor? You see, when we talk about the conductor, then all the charge comes to the surface of the conductor. So in this case, if the charge comes to the surface of the conductor, we had the electric field only going in one direction. When we had the conductor, the electric field was only going in one direction. But in this case, since we have an insulator, you see, if you have an insulator, the charge will not come to the surface. The charge will just stay where it was before, because an insulator cannot allow the charges to move. So it means that the electric field lines can go either outward or inward there. So which area are we talking about? So we are considering this area has got the electric field lines passing. And this area that is inside also has got the electric field lines passing. So if you look at Gauss' theorem here, the flux will involve two areas, this area and an area there. So of course, you are going to realize that the angle will still be equal to 0. The angle will still be equal to 0, because you can see that the area vector for this is in this direction. The electric field is in the same direction, so the theta is equal to 0. The area vector for this guy is in this direction. The electric field is also in this direction, so the theta is 0. So since theta is equal to 0, you can actually remove this electric field from there, from the integral, so that what you just have to integrate is the dA. Now, when you integrate the dA, you find that you have two areas, this area and that area, so you have 2A. Okay, I've seen your hand, Mr. Takati. Let me just finish a bit. So you have this on the left-hand side. What about on the right-hand side? You see, on the right-hand side, it talks about the charge that is enclosed, the charge that is enclosed. So we are talking about the charge that is enclosed there. It's just equal to the area. This is the area, this area that I'm pointing at here, times the surface charge density. So this gives us the total area that is enclosed by this Gaussian surface. So this area cancels with that area. Then the electric field, you just come up with this expression for the electric field. You see that the electric field now has got a 2 in the denominator. It means that the electric field is now half the electric field that was found for conducting sheet. Okay, so Mr. Mpakati, I saw your hand.
Yes, sir. I want to ask about the angle of the electric field and the can you please repeat what the angle?
Okay, can I please repeat what the angle is? So what I was trying to say is that I think I'll answer that question by asking you questions so that I see where the problem is. Are you okay with this electric field, the direction of this electric field? Are you okay? Are you convinced about this, the direction of this electric field? Is Mr. Mpakati there? Hello? Okay, class, are we hello?
Yeah, I can get you now, sir.
You can get me, right? Okay.
Yes, sir.
So what I was trying to say is that this area here, this electric field line, are you comfortable with it? Are you convinced that it's supposed to be in this direction?
Yes, I am.
Yeah, okay with it, eh? So, you know, this electric field is passing through this area here. So what will be there? Flux. Basically, the flux will just be the electric field and the area here. Are we together? Now let us talk about this flux that is going behind. we say that since this is a non-conducting sheet, the charges are not going to only come to one surface, to the upper surface. The charges are going to be distributed everywhere. So it means that the electric field is going to be pointed both to the front and also to the back. So, this is the Gaussian surface, which is a cylinder. So it means that this time there's a difference in that this area that is at the back will also have some electric field that is passing in through there. I'll stop there. Are you okay with that fact? That this back surface will also have some electric field passing through there? Are you okay with that point?
But how, sir?
Pardon? Pardon? Yes, go ahead, Mr. Mbakati. I'm asking you. Huh? Okay, so let us...
Okay, sir, you can continue.
Let us look at this. This is what I've done is that this is the Gaussian surface. I've tilted in such a way that the paper is now here. This is basically just the cross section of the paper. And then this is the cylinder here. This is the cylinder here. So this is the back part. This front part is here. The back part is here. So in this case, the electric field is in this direction. We also have another electric field that is in this direction. Which one is the area vector? On this side, the area vector is in this direction. On this side, the area vector is in this direction. So you see that, what is the flux? The flux here will just be EA, but then there will be another flux here, which will be EA. When you add the two, then what you get is 2EA. There is an epsilon naught that was here before. So now I've evaluated the flux. Now I say the flux must be equal to the total charge that is enclosed. What is the total charge that is enclosed? I'm talking about the total charge that is just within this piece. So I'll say the area of this times the surface area density. And then if you evaluate it, then you come up with its electric field. Okay, so now in this time that has remained, we are going to look at an interesting situation where we have two parallel conducting sheets. Remember, these sheets are conducting. So we have on this side, we have the what? We have, okay, let me just read this. When we have the situation shown in the left, okay, maybe let me just try to give you a picture of what has happened. So this is a conducting sheet. What do you know about a conducting sheet that has got charges? If it has got positive charge on it, then the charges will repel each other. So they'll reside on the surface of this sheet. Remember, this is a conductor. So the charges will reside on the surface. So I have some charges here. Then the charge density, I'm calling it sigma 1. I also have some charges here. The charge density is sigma 1 because they are equal. They are equal charge. So what is the electric field due to this? Remember, the electric field always moves from a positive charge. So the electric field here, it will be in this direction. In a similar way, the electric field here will be in this direction. If I have another sheet here, which is a conducting sheet, and it has got a negative charge, using a similar reasoning, I have some negative charge here, which has got a negative charge density sigma 1, and I have some charges here, which have got a charge density sigma 1. What is the electric field? What are the electric field lines, the electric field pattern? Since these are negative charges, the electric field will be going towards, because these are acting as sinks. Okay, so when these plates are far apart, it means that we'll have this charge distribution as shown here. Okay, now look at the second point there. So here we are saying that when both are in isolation, they each have equal amounts of charge. It means that the surface charge density is sigma on both surfaces, as shown. Now imagine that we start bringing this and this, we start bringing them closer and closer together. We start bringing them closer and closer together. What do you think will happen? What do you think will happen? So something interesting will happen. You see, this charge here was they were separate because of the repulsion. These are positive charges. These are positive charges, so they are repelling each other, so they will reside on the surface. The same argument holds for this part. Now, when we start bringing them together, what do you think will happen? This negative charge here is going to start attracting the positive charges on there. So it means that as we bring them closer, these positive charges that were here are going to start feeling an attractive force that is coming from there. So they will start coming to this inner surface. So that when these plates are closer to each other, then all the charges are going to be in the inner walls because of the attractive forces. So since all the charges that were here are now inside here, it means that the surface charge density is now going to be a sum of this and that, which becomes the 2 sigma. On this side is going to be positive, on this side is going to be negative. Now what will happen to the electric field outside? What will happen to the electric field outside is that it will be 0, because you see that all the field lines that are coming from here are being absorbed by the negative charge in such a way that the electric field outside this is equal to 0. So this is an example of shielding. It means that the electric field has now been shielded. Outside here, all the objects that are outside are free from the electric field. The electric field is just now inside the plate. Okay, so the other argument that you would want to use is that if you construct a Gaussian surface such as this one, then what will be the total charge that is enclosed? What is the total charge that is enclosed by this Gaussian surface? What will be the total charge that is enclosed by this Gaussian surface? Hello? Hello? Are we together, class? Are we together? Hello? In short, what I was saying is that if you have this plate and you have this plate, when you start, if they are far apart, then the charges will be distributed in this way because they are repelling each other. So here there will be positive charges, here positive charges, here negative charges, here negative charges. So as you bring them together, it means that these positive charges here are going to be attracted to the negative charges, so they are going to come on this side. These negative charges that were here are going to be attracted by these positive charges, so they are going to come here in such a way that you have this charge configuration, where here you now have 2 sigma. Because of this sigma, the charge density here, the charges that were here have now been attracted here. Okay, so in essence, what have you done? What you have done is that if you want to find, initially here there was an electric field. Outside here there was an electric field. Okay, but then what is the electric field now? So in order to find out what the electric field is, we consider a Gaussian surface that is here. We consider a Gaussian surface outside, that is outside these charges. Okay, so then you apply Gauss flux theorem. You say that Gauss theorem will say that the flux that is passing through this Gaussian surface, the flux that is, the flux is the outward flux is coming out of here. So what is the flux that is passing? The flux will give you the electric field. Okay, so the flux must be equal to the total charge enclosed. Now, what is the total charge enclosed by this? If you add this is a plus, a minus charge. If you add it with a plus charge, what you get? You get 0. So since the total charge that is enclosed is equal to 0, it means that out here, you not have any flux, you not have any electric field lines passing So the electric field is equal to 0, but inside here you have the electric field. Any questions? Okay, so no questions. Let us answer a question. So the question says that the sketch shows the case of two parallel conducting plates of equal and opposite charge. The sketch shows the case of two parallel. I think actually this one I'll leave it as an exercise for you to think, and then next time when you have found the answer, we can come and discuss. Okay, so the sketch shows the case of two parallel conducting plates of equal and opposite charge, like this. If the positively charged plate has a greater charge than the absolute value of the charge of the negatively charged plate, so this one has got a greater charge, what would be the direction of the electric field in the two areas A and B? So here, is it going to be 0 or is it going to be something else? Or here, is it going to be 0 or something else? When here, there. So try to analyze the situation. I think I'll not answer this question with you. Try to analyze the situation. And then in the next class, if you found some problems or if you want to confirm the answers that you have found, then you can bring it up so that we discuss it together. Okay? So now let us try to do the same thing. Let us try to do the same argument that we have done, where you have these two parallel non-conducting sheets. But then, before they were conducting, meaning that they were conducting. Now we look at the case where they are not non-conducting. Now when you hear non-conducting, what should come into your mind? What should come into your mind is that the charges are not able to move. So it means that even as we are bringing these two plates closer to each other, these charges that are here will stay where they are because it's an insulator. The charges can't move. And these charges that are here, they will stay where they are, regardless of how much you bring these plates together. Okay, so what will happen? So we are saying that in this case, the charges cannot move. So there is no shielding. But now we can use the principle of superposition. Okay, so what does it mean? You know that these charges that are here are producing an electric field in this direction. These charges that are here are producing an electric field in this direction. These charges that are here, the electric field in this direction. The charges that are here, the electric field in this direction. Okay, so as we are bringing them together, it means that these electric fields start overlapping. And eventually, what will happen? Let us see what will happen. Okay, so in this case, the electric field on the left, due to the positively charged sheet. So if you have this is a positively charged sheet, you have this electric field. This electric field is going to cancel with this electric field that is here. This electric field, you see it is to the right. It is going to cancel with this electric field that is coming from this guy. In a similar way, this electric field that is here is actually going to cancel with the electric field that is coming here as we are bringing these plates nearer. Okay, so we're saying that the electric field on the right, due to the negatively charged sheet, is cancelled by the electric field on the right of the positively charged sheet. So what is the result? The result is that the result is much the same as before, with the electric field only in between. So these electric field lines that are here are, because of this superposition principle, the electric fields that are outside here are going to cancel out, and the electric field that is in between is going to be doubled. So the electric field in between here is now going to be double than it was before we brought these plates together. So just try to have some time with yourself. You try to look at this situation, and then you try to go through that reasoning that has been given and see if you can arrive. Okay, so this is just a demonstration now. So you see what we are saying. Let us start. So what we are saying is that this electric field that is here, it will cancel with this electric field that is here. Okay, so this electric field, you see that cancels. This electric field cancels in such a way that outside here, you have no electric field. you just remain with the electric field that is inside here. So the situation becomes similar to the one before. Okay, let me have some reactions here before we proceed. Any questions? Or any contributions, or anyone to say something about what we are learning? Yes, Mr. Mpakat.
Yes, sir. You said that this electric field which is inside will cancel the other one which is in the opposite direction. But how come the electric field is still remaining inside?
Okay. So what did we say? Let me just repeat this animation that is here. Okay. So what is happening is that you see there some component of this electric field. Some component of this electric field here is outward. Are we together? This electric field is outward, but then if you look at this, there is this electric field that is outward here. You must also be looking at the distance. Electric field depends on the what? On the distance, right? So what do you think, as you are bringing these things together, the separation distance here is reducing. Are we together? So it means that
Yes.
a component of this electric field that is here is greater than the electric field that is here because of the distances that are becoming smaller. You know, electric field is inversely proportional to the distance, right? So as you are bringing these closer, you are reducing the distance here. It means that this electric field that is inside here is becoming bigger. But then a component of this electric field, this component in particular, it cancels that component that is here. So it means that this electric field that is here is cancelled completely because this one is weak than the one that is inside here. So whereas this one has been cancelled completely, some of this electric field that is this guy here has only been reduced. In a similar way, you look at this electric field that is here, it will be cancelled by part of this electric field that is here, so that it becomes zero. But since the distances here are smaller, here it just becomes less, in such a way that ultimately the electric field outside is equal to zero, but inside it will not be equal to zero. It will only be twice that which was initially there.
Thank you very much, sir.
Okay. Okay, so I think we are now coming to the end of, towards the end of today's class. And so now let us try to look at an interesting scenario here. So what you can see is that this is a shell. Now these dots that you can see are the charges. So you can call that this as a shell of charge, a shell of charge. Inside here it is empty. Outside here is empty. So there is just this shell that is containing the charge. So now, what is the electric field outside? What is the electric field outside this shell? If you apply Gauss flux theorem, what are you going to say? You're saying that the flux, when you apply Gauss flux theorem, you have to construct a Gaussian surface outside. You want to start with outside. Do you want us to start with inside or outside? Maybe let us decide together. We can find the electric field inside the shell and outside the shell. But let us agree. Do you want us to start with inside or we start with outside?
Inside.
Inside.
We want to start with inside the shell. Let us start with inside the shell. Then we have to construct a Gaussian surface inside the shell. So this Gaussian surface is inside the shell. So as a matter of points, you must make sure that you construct the Gaussian surface so that it passes through the point where you want to find the electric field. So in this case, since we want to find the electric field inside the shell, we must make the Gaussian surface to have a radius that is less a radius that is less than the r. Remember, capital letter R is the shell itself. So now, the flux that is passing through there, according to Gauss' law, the flux must be equal to the charge that is enclosed by the Gaussian surface. Are we together? Are we together?
No, no.
According to Gauss' law, we are saying that the flux that is passing through the Gaussian surface must be equal to the charge that is enclosed in the Gaussian surface. I repeat, according to Gauss' law, we are saying that the flux that is passing through this Gaussian surface must be equal to the total charge that is enclosed in the Gaussian surface. So the question is that what is this charge? What is the charge that is enclosed in the Gaussian surface, which is inside? What is the charge that is enclosed? I think I'm very much interested in this answer. It is what will tell me whether people are understanding.
I can't understand the question. Repeat.
Can you state Gauss' law for me? State Gauss' law. What does it say? I think I won't proceed this class until someone tells me what Gauss' law says.
Hello, doctor. Gauss' law states that the flux of electric field through a closed surface is proportional to the charge enclosed.
Yeah, proportional. What is the proportional is constant? It is 1 over epsilon naught, right? Okay. So
1 over
epsilon naught. Is that okay?
Yes, sir.
So believe me, class, if you can't understand Gauss' law, then all these things that we are talking here are just nonsense. They will not make any sense. The problem with you, some of you, is that you just think that you can just come and attend the class as if you're attending church. You go, the next time you come and attend. When you go out, you must go through these things that we are learning, so that when you come back, we are moving together. Okay? So here the reference that we are using is Gauss' law. So we are saying, you must first of all understand the flux. What is the flux that is passing through the Gaussian surface? The other thing that you must understand, what is the charge that is enclosed by the Gauss, because that is what Gauss' law is talking about. So I'm saying that I want to find the electric field inside. That's what we had agreed. So I construct a Gaussian surface that is inside. So if I construct a Gaussian surface inside, I must be interested in two things. What is the flux that is passing? What is the flux that is passing through that Gaussian surface? And two, what is the charge that is enclosed in that Gaussian surface? So my question was that if you look at this Gaussian surface here, if you look at it, what do you think is the charge that is enclosed in it? What is the charge that is enclosed in it? Yes, Mr. Mtakat.
There is no charge, sir.
There is no charge. Very simple. If you look at that, what is the charge that is inside that Gaussian surface? There is no charge. So it means that the charge enclosed is equal to 0. So it means that the flux must be equal to 0. Now remember, flux is just electric field times the area. So it means that what is the electric field inside? What is the electric field inside? Since the charge, you see, you are saying that electric field times the area must be equal to the charge enclosed. Now you have found that the charge enclosed is equal to 0. So it means that what is the electric field? The electric field will be equal to 0. Because from mathematics, if you have a product to be equal to 0, it means that either one of those numbers that you are multiplying must be equal to 0. Now you know that the area cannot be equal to 0 because this surface here has got an area which is not equal to 0. It means that what should be equal to 0 is the electric field. In short, what I'm saying is this. I don't have the pen today, so we are saying that the electric field, okay, times the area. If you make these two things together, then you have the flux. The flux must be equal to the charge enclosed. Of course, I'm saying that there's also an epsilon note here. If you want, there's an epsilon note. You pardon my writing. It will not be good because, okay? So it's equal to 0 because the charge that is enclosed in this case, I'm trying to look at inside here. The charge that is enclosed.
The screen seems to be stuck.
Pardon?
Hello?
Hello?
The screen seems to be stuck because I can't see your writing.
Okay, because maybe this thing, because every time I do the writing, it can't allow. So I'll just clear all the drawings. But are we able to see why the electric field, just from that explanation, are we able to see why the electric field inside is equal to 0 if you apply Gauss theorem? Because the enclosed charge is equal to 0. Because the enclosed charge is equal to 0, and you know from Gauss flux theorem, electric field times the area must be equal to the enclosed charge. And since the enclosed charge is equal to 0, it means that electric field times area must be 0, which implies that the electric field must be equal to 0. And then now let us come to outside. What is the electric field outside this? You must again ask yourself the question. The question is, what is the charge enclosed? You see that in this case, when you take the Gaussian surface outside, it means that this entire, it means that the entire charge is now enclosed. The entire charge, which is Q, is now closed. So you are saying that the electric field times the area must be equal to Q. Now the question is that what is the area? What is the area of this? The area of this is basically, because it is a sphere, the surface area of the sphere is 4 pi r squared. So if you say the electric field times 4 pi r squared is equal to Q, and then you make the electric field subject to the formula, then you just come up with this expression, which you can see that this is the same as an expression for a point charge that is placed at the center. So it is as good as all this charge is placed at the center, and you are trying to find the electric field at the radius. Okay, so I'm really urging you guys to go through these things in your spare time and try to convince yourselves of these arguments that we are making. So in summary, what we have learned in this PPT that we had started last time, what we have learned is that the electric flux, we have learned about the electric flux is simply the amount of electric field that is passing through a closed surface. The electric flux is simply the amount of electric field that is passing through a closed surface. And then we said that the flux is positive when the electric field is coming out. If you remember this point, the electric field is outward, and it is negative when the electric field is inward through the closed surface. So if you have a closed surface, if the electric field is going inside that closed surface, then we say that the electric flux is negative. If the electric field is going out of that surface, then we say that the flux is positive. And then that led us into Gauss law. Gauss law simply says that the electric flux is proportional to the net charge enclosed by the surface. The electric flux that is passing through a surface is proportional. Let me just go over that again. The electric flux that is passing through an enclosed surface is proportional to the charge that is contained within that surface. So in short, we are saying that epsilon naught times the flux must be equal to the charge enclosed. Okay, this flux can just be written as the integral of the dot product of the electric field and the infinitesimal area vector element. Okay, so there are three geometries that we have looked at. We have looked at the linear charge distribution. So if you have a linear charge distribution, we know that the linear charge density can be given as lambda is equal to the charge per unit area. So now this linear charge density, if you are dealing with a linear charge density, what kind of a Gaussian surface can you take? You must take a Gaussian surface that has got a symmetry which corresponds to a line. What is the symmetry that corresponds to a line? It's a cylinder. So when you are dealing with a line and you are told to apply Gauss law, then you must choose a Gaussian surface that is cylindrical. And when you do that, when you use Gauss flux law that is given there, then you must be conversant with arriving at this expression for the electric field. It means that the electric field at a distance r away from the line must be given by this expression. That is. In a similar way, if you have a sheet or a plane of charge, then you know that the charge density associated with that is the area charge density, which is given by that formula. And what is the appropriate Gaussian surface that you can use? You can still use the cylindrical Gaussian surface. I think we demonstrated on how to do that. And then we came up with two results. The first result is that if that sheet is conducting, then you have this as the expression for the electric field. If the sheet is non-conducting, then you have this as the electric field. The other geometry that we looked at is the spherical geometry. Okay, so now this spherical geometry, if you look at it, it corresponds. Yes, Mr. Mchimba, I've seen your hand.
Yes, sir.
Yes.
First of all, on the sheet or plane.
Oh, yes.
Yeah, yes, sir. Maybe is there a different approach on the infinite sheet and just a sheet?
Okay,
Different approach in terms.
I think that is that's a very good question. Now, that's a very, very good question. That is there a difference between an infinite sheet and a sheet? So, if you imagine that you have a plain paper, a plain piece of paper, as you move away from the plain piece of paper, you move very, very far away. It means that that plain piece of paper, how are you going to start looking at it? You are going to start looking at it as a point charge. With respect to that, to your view, yes, you are going to start looking at it as a point charge. Am I right? Yeah, because yes, you are far away. So it means that even the equations that come, if you look at that equation for the that we had derived using Coulomb's law, you can convince yourself that as you move away, then it will appear as if it's a point charge, and the equation must be that of a point charge. Now, as you start coming closer to it, imagine that you are very, very close to that sheet of paper. Are you going to be seeing the edges of the paper? As you come very, very close to the paper, are you going to be seeing the edges of the paper? So it means that with respect to you, that piece of paper has become an infinite sheet of paper. Okay. And it is only at that point when you can use these equations, because you are very, very close. So these equations are only applicable when you are very close to the sheet of paper. It means that if you are very close to the sheet of paper, that sheet of paper appears to you as an infinite sheet. Has your question been answered?
Yes, sir. Thank you.
Okay. So, now finally we looked at the spherical. Now, if you look at the symmetry of the spherical corresponds to a point. If you look at it in terms of symmetry, you see a point is round. Which corresponds to a sphere. So in short, when you are dealing with a point charge, then you can take, if you are dealing with a point charge, you can take a spherical Gaussian surface, and then you come up with these equations that are here. All right, now, when you are dealing with a sphere, it means that you must take spherical Gaussian surfaces, and then you are going to arrive at these results. Outside the sphere, it means that the radius of the Gaussian surface is greater than the radius of that configuration, that spherical configuration that has got charge. In that particular case, the electric field is just going to be the same as that of a point charge. Inside that spherical charge distribution, the electric field is just going to be proportional to the distance that you move, this radius, the distance that you move from the center of the sphere outward. So it is just proportional to the radius of the Gaussian surface that you take. Okay, so these are the main points that we have learned about in this class, unless there's any question. Any question? Okay, so since it seems there is no, yes, please. Hello? Miss Amchimba, yes, you can go ahead.
Yes, sir. So just on the assignment, you said submission is cut is 17 hours.
So I think we had, I had increased it because we are handing it online. So I had increased the submission deadline up to midnight because I don't have to sit in the office to wait for your submission. You can submit at your own time.
Thank you.
So I said instead of 17 hours, you can submit up to midnight at your. So you can actually it is open. You can submit now or any other time before midnight. Now, if you don't manage to submit after midnight, the assignment will still remain open until something like Monday, if I'm not Sunday, 24 hours, Sunday. But then there will be a penalty attached to that submission. So if you submit after midnight of today, you can still submit because it will not be closed yet. But then there will be a penalty associated with that. And after Sunday, midnight of Sunday, then it will be closed forever. No one will be able to submit. It means that for that assessment, you get a 0. I've seen another hand from Chipego.
Yes, sir. My question is, what can happen to the direction of the electric field if a two electron positive?
Okay, the line is quite very bad. The line is quite very bad. I'm sorry, I don't know if it's possible you can type the question. I could hear some things that what could happen to the electric field, but then I lost. Maybe you can repeat, see if it will be better. Hello, Mr. Chipego. Are you there? Hello? Okay, so it seems he's in a very bad network. Any other questions? Class, are we together? Are we together? Am I online?
Yes, sir.
Okay, so
Yes,
I
online.
think we are going to end our class for today here.
I want to ask you, sir.
Pardon?
Yeah, I want to ask about the videos. I had challenges with the power these past few days, so I couldn't attend the lectures.
Okay, well, well, the videos will be. I said that when I can manage, I'll record them. Sometimes I forget, but I can't guarantee on the production of the videos. I'll try those that I can manage to produce. And the other thing that I don't like about the video is that it makes people not to attend the classes because they know that after all the videos will be provided, which I would not want to encourage. Okay, so I'm going to take it upon myself and see what can be done in that regard. Okay, so I think maybe over the weekend I'll try to edit some of the things and try to put them together and upload and upload them. Okay.
Yes, I appreciate.
Okay. Okay. So thank you very much, ladies and gentlemen. Enjoy the rest of your day, and don't forget next week we have a tutorial. And then, by the way, I'm suggesting that you guys can sit down and tell me whether it will be possible for on Monday, as we are going to be doing the prayers. You can also squeeze in a lecture. So if it will be possible, you guys will tell me in good time so that we schedule for that. Maybe we can have a tutorial then. I'm not forcing you. If you guys sit down and think that you want to have that as a makeup class, then you let me know. Okay. Thank you very much.